you don't need to know he was a professor at Yale, but you better know that equation. This is one of the equations on the equation sheet. And this is what we would do in order to determine spontaneity of any type of process. So again, we talked about enthalpy, that delta H, last semester. I don't know if you have to write all this down, by the way. And how an exothermic reaction is more spontaneous. Because if you can give off heat, then you must have enough energy to do whatever you needed to do and leftover. Last class, we introduced to you entropy, delta S. Entropy is the amount of disorder. According to the second law of thermodynamics, there's a tendency towards more disorder. So you even did a little worksheet where you had to look at phases of things, the number of molecules of things, to kind of determine where is there more disorder. So a positive delta S would give you more likelihood of a spontaneous process. Well, if you take a negative delta H and subtract a positive value, because again, negative is always going to be good for exothermic enthalpy, positive is always good for entropy, that would give you a negative value for free energy. And that is the ultimate determining factor of whether or not something is spontaneous. If this is a negative value, that means you were able to do whatever you needed to do and you gave off energy. Negative values for energy, just like an enthalpy, means the system got what it got done and it gives off to the surroundings. So delta G being negative would make this a spontaneous process. One other thing to mention about this equation, just to remind you, we went over this last time with the reading guide, but we got to be careful with the units on this equation. Again, my hope is this is pretty much plug and chug type math. Very common that in a part A, part B, part C type question, this is down the road. Because you could solve for enthalpy different ways. You're actually going to see us do that one of those ways in the lab next class by doing calorimetry. Entropy, there's not many ways you can solve for entropy. Products minus reactants is pretty much what you're going to end up doing to solve for entropy. But then as you go down those problems that the College Board gives you on the AP exam, then all of a sudden, hey, solve for the free energy. Is this spontaneous or not? So using your answers to the previous letter A and B, you can plug it in and solve. Recall, enthalpy, delta H, is typically in kilojoules per mole. Entropy is in joules per mole Kelvin. That means two things. One, temperature has to be in Kelvin, which we should be used to by now. Ideal gas law, we're used to that. Secondly, though, if this is in a joule unit for entropy and enthalpy is in a kilojoule, you got to make sure the units match up. Again, remember, we don't have a unit test for this 2 days of lecture, but this I know I put on the final. And again, I know that all I'm looking for you to do is plug it in. But I also know that students forget about converting to units. And what's meant to be a fairly straightforward question, we lose a half a point because our temperature was in Celsius. We lose a half a point because we didn't have kilojoules per mole for the same unit. Now, could you have joules per mole? Sure. Gibbs free energy typically is reported in kilojoules per mole, but it doesn't have to be. Okay, just like enthalpy and just like entropy, Gibbs free energy is also something that you can just look up for particular things in an appendix and do products minus reactants, remembering to multiply by their stoichiometric coefficients. And actually, as I look at your equation sheet, under thermodynamics / electrochemistry, the top equation is Q equals mc delta T, which you'll be using next class. And then the next three are all products minus reactants for enthalpy, entropy, and Gibbs free energy. So this is where, again, my hope is I can find the old textbook values and just put them on something for you to see and use for the WebAssign tonight. When I bought a new textbook for us, I was assured that it would be compatible with WebAssign, and then this fall when I try to make that happen, no, that textbook's not available. So that's why we've had to have this issue, unfortunately. Again, I don't think you have to write this down. This is just reminding you of what this means. This is the sum of all the product free energies minus the sum of the reactant free energies multiplied by their stoichiometric coefficients. And our textbook, this is in Appendix 2. And hopefully I can find these values for you guys to help out with that. You guys being first hour, you're kind of the guinea pigs. I mean, you're the ones who showed me that our numbers don't match last time, so hooray, you being first. So there are two more equations on this equation sheet that I need to go over with you. Just so, again, that we are aware of these different equations so we know if we need to use them and how to use them. But the nice thing about Gibbs free energy, and it being kind of at the end of the book, it's supposed to be lightning today and whatnot too, so. The nice thing about it is it actually relates to a lot of different topics. And that's why it's at the end, is it kind of ties in a lot of different things. And that's what you're going to see with these next two equations. We can relate Gibbs free energy to the reduction potential within an electrochemical cell, which we're going to do next class. So you're going to use this equation next class. N is your number of moles of electrons. Like, you know, copper plus 2 electrons. Well, there's your 2. F is something that we actually have already used this year. It's Faraday's constant. And then E is the actual reduction potential. So we will be doing an electrochemical cell next time. Again, the trays that are for your lab are already up against the lab bench. And there's, you know, your U-tubes are already made, ready to go, and we got your solutions. There's strips of metals ready to go as well. So, again, the nice thing about the lab that we do is it's a reminder of old stuff, because that's kind of what Gibbs free energy allows us to do, is to relate a lot of different topics all at once. We can relate Gibbs free energy to equilibrium constants. Now this one, notice it has a capital R. That capital R is the ideal gas law constant, but it's not the 0.0821 value that you use for the ideal gas law. It's the energy version, 8.314 joules per Kelvin mole. T would have to be, again, in Kelvin. Natural log of the equilibrium. There is another equation that can be used to relate Gibbs and the K value that you're going to be using on your lab instead, because this one, once you see that R value for the gas law constant, this one is better used when it comes to gases, and we are not doing a gas equilibrium reaction next class. I did write up on the board when we get time to work on pre-lab, looking over the calculations and things like that, even finding which equations you're going to use. Because if you know which equations you want to use in the lab next time, you know what measurements you need to make. Again, that's kind of an important thing for us to realize. But these two I wanted to introduce right now, because that takes care of the equation section. Again, we should be able to know what these different equations are used for, and recall that on their test they also have on the right hand side then a label of what do these different things mean. So it's not like you have to memorize this R value, although there is more than one R value that is used within gases, so you just have to know which one to use and when, which sometimes is a little tricky, I suppose. Okay, we don't need to remind you the K value, we know what that is. All right, here is what we're going to end with today. My people in the front row, maybe, are lucky enough to get to do this experiment. We are going to figure out the entropy of a rubber band. Seems like an odd question, but I found this somewhere once, and I'm like, yeah, let's do this. Here's Gibbs free energy. So we can use this to solve for something other than delta G. We can solve it for delta S, which I believe is what we're doing in the lab next time as well. Is that we are going to use calorimetry to solve for our enthalpy. we're going to use the voltaic cell to solve for our delta G, and then we can solve for delta S. So I'm going to rearrange this equation in this form. Okay. Boy, that takes a long time. I mean, it looks cool. Kellen, you know what your fill term is? It's this right here. It's the one part I don't think I can really grow a mustache very well. Looking just alone as a gap would be weird. Okay, you ready, front row people? You're going to stretch the rubber band out, and you're going to place it against your fill term. Now, you can smell the rubber. There's no doubt about that. But is there anything else that you can feel? Does it feel colder? Does it feel warmer? A little bit warmer. Okay, so you can unstretch that for a second, unless you want to just go to hold that in place. It should feel a little bit warmer when you do that. And you guys at home can do this as well. Sorry, I only have so many rubber bands, and I didn't want to exclude the people in the back. So I just excluded everybody except for the front row. Okay, hopefully this second statement makes sense. Stretching the rubber band is not spontaneous. This rubber band did not extend on its own. The three people in the front and myself had to put energy in to make this happen. And if this is not spontaneous, that means my delta G value would be, is it positive or negative? Positive. A positive delta G is not spontaneous. In thermodynamics, a positive value means energy is put in to the system to make it go. We had to put energy in to make this stretch out. It did not do it on its own. So we know that that is a positive value. If they felt, it wasn't a lot, but a little bit, and this was with a fairly thick rubber band, the thicker the rubber band, the more you can tell. If they felt it getting warmer on their fill term, does that mean that delta H is positive or negative? If they felt the heat from this, negative, heat's given off. When you feel warmth, that means something else is giving off that heat. Just like if you touch something and it feels cold, it's gaining heat from you. So, we have just determined that the enthalpy is negative, it's exothermic, and the Gibbs free energy is positive. If you look at this equation then, if I take a negative minus a positive, I am guaranteed to get a negative value. Does that make sense? Not everything with this equation has to be built in with numbers. Sometimes it's more of a, hey, what if this value is positive and this value is negative? What am I going to get as an end result? If entropy is negative, that means when this is stretched out, it's actually much more orderly than when it's at rest. And we can do the exact opposite. So you three, ready? Stretch it out. Then, what you're going to do, if this eventually gets across, relax it and then put it up against your lip. Doesn't feel warm anymore, right? Now it feels cold. So when they did the exact opposite, it felt colder. When it feels cold, that means endothermic. It's taking in heat from them. When you let go of a rubber band, it unstretches spontaneously. There's no energy needed for that to go back to its original position. So letting go of the rubber band would be spontaneous, so our delta G would be negative. That means how rubber molecules and rubber bands are formed together, they're actually more orderly when it's like this, and less orderly when it's like this. That's kind of the numerical proof that we can do with this. Again, I bring up this example not because we're going to ask you about rubber bands, but because we can use this Gibbs equation, yes, to just plug in and solve. But we can also use this equation to, in general, figure out the spontaneity of things. If you know if it's exothermic or endothermic, if you know whether or not it is more disorder or less disorder, which we went over last class, you could just look at phases and the number of molecules to determine that. So ultimately, you could solve for delta G without even doing numbers of whether it's spontaneous or not.